Alright, so in this video we introduced the cross product. So we mentioned earlier that there are two ways of doing multiplication vector to another vector. One of them is dot product and the other one is the cross product. While we're here, vector dividing one vector by another is not defined. So given any two vectors A and B, we define the cross product as follows. So it's defined by a 3 by 3 determinant where the first row is occupied by the unit vectors I, j, and k. Second row is occupied by the components of a, x, y, and z component, and this third row is occupied by the components of b. Alternatively, the cross product is magnitude of a times magnitude of b times the sine theta, where theta is the angle between a and b. Remember, for the dot product is what it was cosine theta here. But in addition, because this is a scalar, this is a scalar, and this is a scalar, there is a unit vector u, because the cross product is also called the vector product, because the resulting the output of a cross product gives you a vector. So this makes sure that this term is a vector here. So the u is a unit vector. So this is how this works. So a cross product is going to give us a vector perpendicular to both a and b. So if a and b are in this plane, so suppose a and b are in this plane here, so imagine that this is a, the vector a, imagine this is vector b, they are both in this plane. Okay, then a cross b is going to be a vector perpendicular to this plane, so it's going to be a vector outside, going outward of this plane in a perpendicular manner. So that is going to be a cross b. So this vector is perpendicular to this plane, which means it's a vector perpendicular to both a and b. And as we are going to see in a moment, then b, a cross b goes upwards, then b cross a is going to go downwards. Okay, so cross product has got lots of application. I'm just going to mention one application in electromagnetic theory. So if you have a wire which is in this plane, okay, make sure this looks like a wire, and the current in the wire is going in that direction, and you apply an electric field in this direction here. That's your electric field, that's the direction of the current. Okay, then the wire is going to move, and the direction of the movement is going to be in the direction of the cross product of the direction of the current and the electric field. I mean the magnetic field. So imagine this is the magnetic field direction, which is typically denoted B. Okay, so electric current is going this way, a magnetic field is going that way, then the motion of the current is going to go that way. So if you have got direction of current, direction of magnetic field, then the direction of the motion is going to be given by the cross product of the two. Similarly, if you have got the motion and the magnetic field, you've got a current in a magnetic field, and then you move, then the direction of the current induced is going to be determined by the cross product. Alright, so that's just one application. Let's look at the properties of the cross product. Alright, so now for some properties of the cross product. The first one is that A cross B is the negative of B cross A. So if you switch them, then you incur a negative. So just remember, the negative of a vector gives a vector in of the same magnitude in the opposite direction. So if this is vector V, then that is going to be negative V. Also remember that the vectors are independent of the spatial location. So if this is V here, that's going to be V there, going to be V there, so long as they have the same direction and magnitude. Okay, so that's that. But of course, from matrix theory, you're going to remember that if you've got a determinant and you switch two columns or two rows, then the determinant is negated. So that's another way of thinking about this first property here. The second property is that the cross product of A and A is 0. So again, if we go back here, if we use this one, or if we go back here, from matrix theory, the determinant of a matrix with two rows that are identical is going to be 0, or columns that are identical. But another way of looking at it is the fact that the angle between A and A is 0, and sine 0 is 0. And then lastly, notice that this 0 is underlined, so that means it's a 0 vector, and 0 vector is like this, as opposed to a scalar 0. So that means it's a vector whose three components are all zeros. Alright, well, from here, then I cross I is going to be equal to J cross J equals to K cross K, and all of them are going to be 0. Okay, and then on the other hand, I cross J is K, J cross K is I, and K cross I is J. Okay, this is called a cyclic group. You might meet this in your abstract algebra. Okay, so it's an example of a cyclic group. Fifth one, there is a similar property we looked at on the dot product. If A cross B is 0, but neither A nor B are 0, then A and B are parallel. So the cross product is going to tell us when two vectors are parallel. The dot product, we can use it to check if two vectors are perpendicular. The last property here the magnitude of A cross B gives us the area of a parallelogram whose two sides are A and B. So if we've got a parallelogram here, so that's parallel to that, that is parallel to that. Okay, so if this is vector A and this is vector B, then this area is going to be given by, we do A cross B, then we take the magnitude of that. Okay, let's look at some examples that involve the cross product. Right, in the first example, we have got vectors A and B. We want to find the cross product A cross B. A is 7i minus j, B is 9i plus j minus 4k. So let's see how this works out. So A cross B. So we're going to slot these into this 3 by 3 determinant. A is 7 minus 1, 0. B is 9, 1 minus 4, 9, 1 minus 4. Well, there is a number of ways we can do this. We see there is a 0 along this column or along this row. I'm going to evaluate this along this column so that we only have two determinants to work out. So remember, plus minus, so that's plus, and then it's going to be times this determinant here. Plus minus plus minus plus, it's going to be minus 4, going to be times the determinant ij 7 minus 1. This is going to be 7 plus 9, so it's going to be 16k minus 4 into, this is going to be minus I minus 7j. Okay, so this is going to be 16k plus 4i plus 28j. If you like, we can write this. The x component is 4, the y component is 28, the z component is 16. Although of course we can leave it in that form, it's completely acceptable. Okay, in number 2, want to find the exact area of a triangle with vertices A, B, and C. They are specified. So I'm just going to make a little sketch here just so that we appreciate what's going on. It's going to be a very rough sketch because of course it's impossible to do justice with this type of thing, because these coordinates are in 3D space. So 1 to 1 is the coordinates of A, B is 2 minus 2, 0, 2 minus 2, 0, and then C Let me put here. C is -2, -5, -3. -2, -5, -3. So this is the this is the triangle for which we want to find the area. Now, in order for us to find the area of this, we are going to have to express two of these sides as vectors. Okay, now from that property, you are going to remember that so what we're going to do is if we extend this to be a parallelogram, if I take this side and put it there, and then this one I put it here, then all of a sudden you can see that we've got a parallelogram. But of course the area of the triangle we're interested in is simply going to be half of the area of the parallelogram. So if we express this as a vector, so that could be vector AB, and then this could be vector AC. Okay, so vector AB, we already talked about this in the first video. We are going to do coordinates of B minus coordinates of A. Okay, so for the x component it's going to be 2 minus 1, which is 1. For the y component it's going to be -2 minus 2, which is -4. And the z component is going to be 0 minus 1, which is -1. Then AC, we do coordinates of C minus coordinates of A. X component is going to be -2 minus 1, which is -3, -5 minus 2, which is -7, -3, -1 is -4. Okay, then we're going to do AB cross AC. So IJK 1 minus 4 minus 1, -3 -7 -4. Okay, this time I'm going to do them just in the I'm going to expand this along the first column. So for the first one, it's going to be 16 minus 7. What's 16 minus 7? So this is 16, this is 7. 16 minus 7 sounds like 9. And then for the second one, instead of major minus minor, I'm going to do minor minus major. Is going to be 3 plus 4 is going to be 7, and I'm going to put a plus here. So 3 plus 4, yes. Then for the last one, we are going to have -7 minus 12. It's -7 minus 12. Sounds like -19. 7, 12. So this is the cross product A B cross AC. So the area of the whole parallelogram here would be the magnitude of this, but we're only interested in the triangle ABC. So that's going to be half of the area of the parallelogram. So when you say area is 1/2 magnitude of AB cross AC. So that's going to be 1/2 Magnitude of that is square root of 9 squared plus 7 squared plus 19 squared. And then we can punch that in the calculator. So 9 squared plus 7 squared plus 19 squared. 9 squared, 7 squared, 19 squared. 19, not 16. That's 491. So it's going to be 1/2 491. Just part of interest. Let's see. Well, this is clearly not divisible by 4. Is it going to be divisible by 9, which is the next square number, divided by 9? No. Okay, so we're just going to leave it as 1/2 of square root 491. Right, in the next video we're going to look at triple vector products, and 1 or 2 applications, maybe a proof, and then yeah, that will cover the basics of vectors, vector algebra.